Hey guys, welcome back. Today we're going to learn about capacitors, and mostly we're concerned about capacitors in alternating current, but in order to figure out how a capacitor might behave in an alternating current circuit, we have to look at how it behaves in a direct current circuit. So for right now, we're going to start by just figuring out, what is a capacitor, how does it work, how is it built, and why does it behave the way it does, and then we're going to start to put capacitors in AC circuits and see what occurs. I know you guys know something about capacitors because you've probably been using them in electronics as filters, and so let's take a look at a capacitor. Now, the first thing you've got to know about a capacitor is that it is actually a very simple device. It's, we all have enough equipment in our kitchens right now to make one. It's simply two metal plates, and I'm going to draw them as lines here, but imagine these being pieces of tin foil or cookie sheets or something like that. Two conductive plates with some leads connected to them, and then inside or in between those two conductive plates there's an insulator, and that insulator has a special name. It's called a dielectric. Okay, now that's all there is to it. And you would think that if you connected it to a DC circuit with a switch like this, that if you close the switch nothing would occur. But actually what occurs, and I'm going to be electron flow for a minute. I'm usually conventional current flow, but for right now I'm going to be electron flow. We're going to see what's going to occur with the electrons as we close this switch. What happens? Maybe I'll put a resistor here just for fun. All right, and we'll make some determinations as to how it behaves. So first thing you got to know about this source is that this is the positive post and this is the negative pole, I should say. And this is negative because it's got a surplus of a negatively charged electrons here. There's negatively charged electrons on this side as well. Everything is negative, but there's a lot less negatively charged electrons here, and so there's a shortage of electrons here, which is why we call it positive. Here there's a surplus of electrons, which is why we call it negative. And if I close this switch, what actually occurs is a bunch of these electrons, there's a big surplus of them, they whip around here, and they all start to actually stack up on this plate over here, like this. And that has the effect of repelling electrons that might be over here, plus there's a shortage of electrons over here, and so some of these electrons that are kicking around here, the free ones, they'll start to make their way around here, and this will become positively charged. And if I look at what that looks like over time, well, let's draw a little Van Andel timeline here. So what we're going to do is maybe put an ammeter in here. Okay, so this is my ammeter. We're going to put a voltmeter across here, and we're going to determine what the voltage and the current looks like as I open and close that switch. And so let's say the switch is open for right now. If the switch is open, there's nothing going on, and the voltage would be 0, and the current would also be 0. But let's say right here, I close that switch. What happens is, as soon as I close the switch, that's when all these electrons move. And so I get this, spike of current that looks like this. But as those electrons make their way around here, soon this starts to fill up with any available electrons. All the electrons that want to leave here do slowly leave, and so the current, tapers off and eventually becomes 0. And now, once this all happens, sort of the current, stops flowing. If I take a look at the voltage at the same time, let's mark that current here. Put a voltmeter across this capacitor. What I see is, as those electrons are making their way over here and these ones are leaving, the potential difference across that plate is increasing, and so I get this curve that looks like this. Okay, and that is the voltage curve, and that eventually becomes equal to whatever this DC source is, and then nothing changes anymore, and I don't have any current flowing anymore, and the voltage potential across the capacitor is equal to the source voltage right here. And this is what we call, charging the capacitor, right? Now, if I took a look, well, first of all, if right over here, I suddenly open that switch, let's do that for a second. Let's say right here, I open the switch. If I actually do that, so I close the switch, I've charged the capacitor, it's fully charged now. Now I'm going to sit here and open the switch. What will actually occur is absolutely nothing. Okay, the voltage that was, all these electrons have made their way over there. All these ones are gone. If I continue to measure the voltage across there, even after opening this switch, the voltage will remain equal to the source voltage. In fact, I could take this capacitor out and put it in my lunch pail and, bring it home and measure it after supper. It would still measure whatever the voltage was that I used to charge it up to. And same with the current. If I open the switch, the current is going to remain zero, obviously, because the switch is open. Now, what I could do is try to discharge this capacitor, and I don't have enough in this circuit right now to discharge it, but let's say I added a switch right here from there to there, and now with this switch I could close it and try to discharge this capacitor. And so right here somewhere I'm going to maybe discharge the capacitor. What I would see is, well, first of all, if I'm electron flow, the current flowing through here to charge it up went in this direction. When I close it, all these electrons will make their way around here and try to come over to here to equalize it. And so notice that when I close this discharge switch, the current will start to flow in the opposite direction. So right here, when I discharge this capacitor, I'd get this big spike of current again, which would, taper off because eventually all these electrons would make their way around there. And I would also see the voltage, coming down like that. Right, guys? And now this thing is discharged. Now, before we go any further, you probably already know from your electronics class that this charge curve and this discharge curve is very predictable. And I'm not going to spend a lot of time on it, but I want to remind you that this charge curve can be split into 5 sections. Let's see if I can do that here. Each one of those is called one time constant. And there's a formula for calculating that time constant. If you know the value of the capacitor in microfarads and also the value of resistor in ohms, it is this formula right here. T is equal to RC. And so, if this was 350 microfarads and this here was 1,000 ohms, I could calculate exactly how long one of those time constants is using this formula right here. And so let's try it. T, one time constant, should be R, 1,000, times C, and the value of the capacitance must be in farads, and since this is 350 microfarads, in order to convert it into farads, I'd have to move the decimal place to the left 6, and so it becomes 0.00035 farads. And if I do that math, 1,000 times 0.00035, I get 0.35 seconds. And that would be the amount of time it takes to, get from here to here, one time constant. There is always 5 time constants in order to fully charge a capacitor. So in order to calculate the charge time, it's always equal to T times 5. And so in this case, it would be 0.35 times 5. And this particular setup would take 1.75 seconds to fully charge. And by the way, this rule here, for this formula for calculating how long it takes for a capacitor to charge is the same formula as the one that you would use to calculate how long it would take to discharge a capacitor if you knew the value of the capacitor and also the value of the resistor in series with it. Okay, so it works for charging and discharging. The discharging is also going to be split into 5 sections, each one called one time constant. So you can always predict T by calculating or multiplying the resistor times the value in farads, and then multiply it by 5 to calculate the total charge or discharge time. And by the way, I know you guys know this already, but just a reminder, one time constant will charge the capacitor to 62.5%, 63.2% fully charged. Okay, so in other words, if I went up here, I would notice that it would be 63.2% charged after 1. The second time constant is going to charge it to 63.2% of what's left over. Same with the third one, 63.2% of what's left over. Same with the fourth one. And after 5, it would be considered to be fully charged. Stick around for the next video on capacitors.